Today is all about logistics networks and facility location. So we can look at some simple tools that will help us determine optimal location for our facilities. This could be manufacturing facilities, service facilities, or behind the scenes things like warehouses and distribution centers. So we have to determine which of our facilities are sensitive to location. Do I need to be near my customers? Do I need to be near the local port? Do I need to be in a particular country? Like what part of the location is sensitive? And then I go from there to optimize my decision factors. In manufacturing, I'm looking at all sorts of things from labor rates to labor laws to whether or not the labor is skilled enough for my manufacturing needs. How close am I to markets? Or how close am I to my suppliers? What is my impact on the environment? This could be water and electric use. It could also be the actual land that you're looking at locating on and local environmental regulations. You have to look at how close you are in proximity to your parent company facilities, if that's important, and things like cost of real estate, taxes, regulations that would come into play in locating in particular, whether it's countries or cities and states within countries. Within services, location to your ultimate customer might be even more important. So, is the customer coming to you or are you going to them? So, proximity to customers, transportation cost, location of competitors, if that matters. And then, of course, site specific factors like taxes, regulations. So, there's a couple different mathematical methods we can use that will help us determine our optimal facility locations. I will take you through some simple perspectives on looking at some different options. So let's talk through what the load distance method shows us. This is a mathematical method that looks at locations based on a couple of different factors. There are two different types of distances we can use when calculating load distance scores. The Euclidean distance is a straight line distance. So it's basically what I would call a bird's eye view, or as the crow flies between two different locations, which is simply the square root of your two x locations squared plus the two y distances squared. So you have this straight line factor that's giving you Euclidean distance. Compare that to a rectilinear distance where you're actually taking into account turning. So 90-degree turns to get from one facility to another. So this is helpful when you're looking at trucking routes and turns for actual infrastructure of your transportation. So we just want a general proxy of distance between places. The Euclidean distance is probably a sufficient proxy, but if you're looking for specific trucking routes or optimizing that, you would want rectilinear distance. So when we calculate a load distance score, this will vary by industry, but we're basically looking at among my different locations, and this could be locations of suppliers or locations of customers. How dense is the load need? And then what is the sum of those different options? So let's say I have 3 different cities that I am sending products to. How much demand is there in each city, and how far away are those cities from me? That will help me determine a load distance score. But maybe I don't have my location yet, so I want to determine a center of gravity to figure out where my optimal location is. So this is helpful when you're planning new facilities, like new manufacturing, new warehousing, new service sites. And you can figure out your centralized place. So centralized to suppliers or centralized to customers by doing a center of gravity calculation. So our overall center of gravity calculation will have both an X and Y coordinate. You can think about this in some ways as like latitude and longitude. So it's a location coordinate, and we're looking at the sum of the load. So it could be like the population density of a particular area times the x coordinate of each area divided by sum of total load. We can do the same thing for the y coordinates. So we have x and y. The simple way to think about it is latitude and longitude, though there can be other grids you could apply. Let's walk through an example that I think it'll help make sense of these calculations. So we have a supplier here to the electric utility industry that produces power generators. Transportation costs are high. So one market area includes the lower part of the Great Lakes region and the upper part of the southeastern region. And there's more than 600,000 tons that are shipped to 8 major customer locations. So we have these 8 major customers. You can see the locations listed. You also see the load. So this could also be termed demand in each location. So tons shipped. And then we have X and Y coordinates for each location. So we're going to try to figure out a center of gravity amongst our customer options. So our center of gravity calculation has a couple components to it. The first component is simply the sum of the loads in each location. So you can also think about this as the sum of your customer demand in that region. So in this case, we have tons shipped. And so if you add up all these tons shipped, you'll notice this formula here is the same numbers, but without the thousands. So the number is truncated. So we've got 5,000, 92,000, 70,000, just like in the table. We add them all together and we get 607 or 607,000 tons. That's a total demand in this region. But now we're going to break that up into the score that's the sum of each customer location's tons times its appropriate coordinate. So we'll focus on the x coordinate first. If you notice up here in the table for Three Rivers, Michigan, you've got 5,000 tons, and then your x coordinate is a 7. So if you go down here to where we are multiplying those together, we have 5 times 7 as the first term. If we move on to Fort Wayne, you have 92,000 tons times an x coordinate of 8, 92 times 8. And we continue that for all of our different customer locations, and then we ultimately sum those together at the end, 7,504. We'll then do our x star calculation, which is the x coordinate of our center of gravity. And that's going to be our 7,504 divided by the sum of our total loads, 607. And then that will ultimately get us to 12.4 as an X star location. We'll do the same thing for the Y side of the coordinates. So in this case, Three Rivers, Michigan, we've got 5,000 tons. The Y coordinate is 13. So you'll notice the first term here in this equation is 5 times 13. For Fort Wayne, Indiana, you've got 92,000 times 12. So 92 times 12 is the second term here. We continue through all of our customer locations, focusing on that Y coordinate, and we get a sum of 5,572. So to calculate our Y star, which is the Y coordinate of our center of gravity, we have 5,572 divided by the sum of our total loads, which is back on that previous slide, 607,000 tons, gets us to 9.2. Now that we have a center of gravity, that gives us a starting point that's centralized to not just centralized based on distance, but centralized based on the customer load or customer demand for each of our customer locations. So we can actually calculate a resulting load distance score based on that center of gravity. And that load distance score is looking at the sum of all of our load and distances of each of our particular locations, where the distance is the difference between the x coordinate but that location minus the center of gravity plus the y coordinate for that location minus the center of gravity. So if we look at our center of gravity, go back, the x coordinate is 12.4, the y coordinate is 9.2. So for our distance from Three Rivers, Michigan, we would have 7 minus 12.4 plus 13 minus 9.2. Right, 9.2. Okay, those are absolute values, so you don't consider the negative. The negative is stripped away, and the total sum is added together. So for our low distance score, the first term is what we just calculated, 5.4 plus 3.8, summed together, multiplied by tons shipped out of Three Rivers, Michigan. And we'll do that for each and every customer location, calculating this distance, x and y distances added together, and then multiplied by the load for that customer location. Your total sum of these calculations, 2,662. So you can actually look at the center of gravity where you are, and then you can see where all your customers are located. Notice that the center of gravity is weighted by demand as well, or load. So this can shift around. If you change the demand or the load, that center of gravity will shift around as well. But this gives you a good idea of where a new facility could be located and have the benefits of being centralized. We can also look at things like a break-even analysis. This considers both fixed cost and variable cost in a new location. And when real estate prices vary widely in locations, or labor rates vary widely, a break-even analysis can help you determine the differences between different options. So here's an example of a break-even analysis. We have management that narrowed the search for a new facility location to 4 communities. We have annual fixed cost, which are things like land, property taxes, insurance, equipment, the building, and variable cost, which are labor, materials, transportation, any variable overhead. So as a reminder from business school basics, fixed costs are fixed. Whereas variable costs are usually a per unit cost analysis. So the more units you make, the higher your variable costs. Fixed costs are fixed by definition. Okay. So we've got our 4 different communities, A, B, C, and D, fixed cost for each one. You'll notice if you have a lower fixed cost, you typically have a higher variable cost. That's true generally speaking. So we have fixed cost and variable cost. Variable cost are per unit. So we want to look at a break-even analysis for all of our community options and identify at what volumes are optimal, knowing that the expected demand is around 15,000 units a year. So we're looking at a range around that. What is the best location? So we're going to plot this plot this problem on a total cost line, ranging from volumes of 0 to above our expected value. We said expected value was around 15,000, but we're going to take the graph up to 20,000 just to show the total range. When we are plotting total cost lines, your fixed costs are basically your intercept point of the y-axis, and your variable costs are per unit. So the slope of your line is determined by your variable cost. For community A, we had $150,000 fixed cost. Our variable costs are $62 per unit. So if we plug in 20,000 units, we'll get variable cost of 1.24 million. If we add the fixed cost to that, we'll get a total cost of 1.39 million for total cost. We could do that for each of our particular communities. And that will ultimately bring us to our graph that shows all of our options on a single graph. Now, as I mentioned, the fixed cost amount is your intercept. So if you'll notice where all these lines are touching the y-axis, that is your intercept point. The slope of the line is your variable cost. So line A here has the steepest slope. It also had the highest variable cost. And your point here is your total cost in millions, 1.39 million, as we mentioned earlier. So what you can see, because this is a total cost graph, so you want to minimize total cost where you can, save some money, of course. So A is our best option at low volumes. It has the lowest total cost. But then where we cross over to where B is the best option for intermediate volumes, and then we cross over another break-even point to where C is the best option. So we know that there are some ranges where the decision is different between A, B, and C. And we can actually calculate what these break-even volumes are. So the break-even quantity between A and B, you simply take the fixed cost, $150,000, plus the variable cost, $62 times Q, in this case, quantity, and you set it equal to the break-even equation for the next option, in this case, option B. So the fixed cost is $300,000 plus variable cost $38 times Q. I take these two equations, they were set equal to each other, and now I solve for Q. So I rearrange terms and divide and solve for Q. I get Q as 6,250 units. So that is the break-even volume from when the decision changes from option A to option B. I can do this calculation again to determine the difference between options B and C. So I take the break-even equation for option B, 300,000 plus 38 times Q. And now I set that equal to the equation for C, which is a $500,000 fixed cost plus a $24 variable cost. I solve for Q, and I get Q as 14,286 units. So that is the break-even volume from changing my decision from option B to option C. Now, as we can see, based on the slope of the line, option C will be my best choice in terms of cost for any volume above 14,286 units, which is why no other break-even quantities are needed, because I know I'm either going to choose A, B, or C based on my expected demand.